Imagine trying to teach a computer to understand human language. One of the very first hurdles we face is how to represent words. Should we treat every single character as a unit? Or every complete word? Both approaches have significant drawbacks. Character-level encodings miss out on semantic meaning, while word-level encodings struggle with new, unseen words and create incredibly large vocabularies. This is where byte pair encoding, or BPE, steps in, a clever algorithm that offers an elegant compromise. BPE is a data compression technique originally developed in 1994, but it found its true calling in the world of natural language processing, especially with the rise of deep learning and transformer models. At its heart, BPE is deceptively simple. It iteratively finds the most frequent adjacent pair of bytes or characters in a text and replaces that pair with a new, single, unused symbol. This process continues until a predefined vocabulary size is reached, or no more pairs can be found. Let's start with a very simple example. Imagine we have a small corpus of text containing words like low, lower, lowest, newer, and wide. If we begin by breaking everything down into individual characters, our initial vocabulary would consist of L, O, W, E, R, S, T, N, V, D. Now, BPE begins its search. It scans the entire corpus to identify which pair of adjacent characters appears most frequently. In our hypothetical example, it might find that low is the most common pair. Once low is identified as the most frequent pair, BPE merges them into a new, single token, let's say low. Now, every instance of L followed by O in our text is replaced by this new low token. Our vocabulary now includes low. The process then repeats. With low now a part of our vocabulary, BPE scans the text again, looking for the most frequent adjacent pair. Perhaps L now emerges as the most common. It would then be merged into L, and so on. This iterative merging continues. Each step creates a new subword unit by combining the most frequent adjacent pair. The algorithm typically stops when a desired vocabulary size is achieved. For instance, we might decide we want a vocabulary of 30,000 unique tokens. Alternatively, it might stop when no more pairs exceed a certain frequency threshold. The resulting vocabulary is a fascinating mix. It will contain all individual characters, along with common subword units like ing, un, ed, and even full, frequently occurring words like the or and. Less common words might still be broken down into their subword components. One of BPE's major advantages is its ability to handle out-of-vocabulary, or OV, words. Since every word can ultimately be decomposed into individual characters present in the vocabulary, BPE can always represent any word, even if it's never seen it before, by breaking it down into its known subword units. This dramatically reduces the unknown word problem. BPE has become a cornerstone in modern natural language processing. It's widely used in large language models and transformer architectures for tasks like machine translation, text generation, and sentiment analysis. Its efficiency in creating a balanced vocabulary, managing rare words, and reducing computational overhead makes it indispensable. However, BPE isn't without its limitations. The purely statistical approach means it doesn't inherently understand linguistic meaning. Sometimes, merges might create tokens that aren't semantically intuitive. Furthermore, the final tokenization can be sensitive to the initial training corpus, potentially leading to different tokenizations for the same word across different models. To illustrate its power, consider a new, never-before-seen word like unbelievable. A well-trained BPE model, even if it hasn't seen this exact word, would likely break it down into meaningful subword units like un, believe, and able, because these are common morphemes it has learned to merge. In essence, byte pair encoding bridges the gap between character-level and word-level representations, providing a flexible and robust way for computers to process and understand the vast complexity of human language. It's a testament to how a simple, iterative process can yield powerful results, underpinning much of the AI revolution we see today.